Hi, Mrs. Spohn here, continuing our torque video series. This should be video 2 of 3 or 4. And what we're going to do is we're going to look at some torque problems, just some simple math problems involving torque. I wanted to start with this cool little picture. This almost looks fake, but I can assure you it's not. You can actually do this at home. All you need is a ruler, a hammer, and either some string or a cable tie, or just something to tie the hammer in that fashion. So what's going on in this picture? It's actually a combination of torque and center of mass. We talked about center of mass already. We know that objects rotate about their center of mass, and they don't tip over until their base is outside, or their center of mass is outside of their base. So we know the weight of the hammer goes down. The center of mass is about in this area right there for the hammer. What happens is the string, because the hammer wants to go down, but the string prevents it from doing so. So the string acts as a axis of rotation. So as the head of the hammer is pushing down, it's going to kind of rotate the butt of the hammer up, and it's going to actually push against the ruler. So that's one way to kind of look at this in terms of torque and free body diagrams. There are some other forces we're missing, but basically that's why the ruler, which naturally on its own would fall off the table, but it doesn't in this case. The other way is to consider center of gravity. One, we know the hammer is more massive than the ruler, so the center of mass is pretty much going to be with the head of the hammer. And as it turns out, you can't really see it in this image, but the center of mass is underneath the table. The center of mass is not outside the confines of the table. Otherwise, this system would fall. Since the center of mass is within the confines of the table, it's underneath the table, some point right underneath it, there is no net torque outside, and this hammer will not fall. And recall that objects do not tip until their center of mass is outside their base. So you have the Leaning Tower of Pisa here. You look at the center of mass and the arrow drawn downwards. As long as that arrow drawn downwards is within the confines of the object's base, it will not tip. So this object's not tipping. In case you think this is a trick of the internet, this is a very simple demonstration to do that you can do at home. I could have just put that on the edge of a table or a desk. So I encourage you, just try it at home. Little torque experiment, torque center of mass, little basic physics. You can come up with some really crazy contraptions with forks and other things. You do a little research on the internet. Give it a try. Build something related to torque. All right, so let's go on to some math magic, some physics. So we're going to deal with torque in terms of seesaws. You have two people sitting on opposite sides of a seesaw. They have different weights. The lady on the left weighs 300 newtons. The gentleman on the right weighs 400 newtons. So if they sat at exactly the same distance on each side, obviously the seesaw would tilt towards the heavier individual. So what we need to do is we need to have the heavier individual move relative to the lighter individual, so that way the torque on the left can balance with the torque on the right. The only way to have this seesaw perfect is if torque on the left, obviously the weight of the lady is going to generate rotation of the seesaw down. The weight of the gentleman on the right is going to rotate a torque down that way. So what we need is those two forces basically to balance. We need the torque on the left to equal the torque on the right. And we know the formula for torque. Torque is force times distance, or force times radius. So we need the force times radius on the left to equal the force and the radius on the right. And this becomes a pretty simple problem because we are given three variables. And this is really, really simple. We are given the force on the right, 300 newtons. We know the radial distance on the right, 4. We also know the weight on the right, 400. All we have to do is solve this equation for r on the right. And if you do that, 300 times 4 is 1200. And that equals 400 times r. And it's just going to turn out to be 3. This is a problem you can do. We're going to do a few more out in full. But really, you just plug these numbers in. 300 times 4 equals 400 times whatever this is. And you solve. And it turns out to be 3 meters. And this is how mass was measured for a long time, using balancing and basically a scale system in that sense. So keep that in mind. That's just your intro to torque. Torque on the left equals torque on the right. So here we have another problem. We have Fred and Barney. Freddie Flintstone, weighs a lot more than Barney. He's 3 times as massive in this problem. So Fred is 150 kgs, which mass times gravity we know is 1500 newtons. Weight is down. Barney is 50 kilograms, which is 500 newtons. His weight is down. We just don't know where to put these arrows yet. We don't know where to put these individuals. They're playing on a very long seesaw. Seesaw is 6 meters. They want to balance out perfectly. Where should they sit? So We don't know where to put them yet. We want to figure out where to put them. We know that if we put them equidistant on opposite sides, we're going to tilt towards Fred, but we want to balance perfectly. So where do we put them? And there's another question down here too. Where is Fred's maximum distance to keep the system in balance? We'll talk about that at the end. So first off, just looking at the formula, force times R, or force times distance on the right, must equal force times distance on the left. Force times distance on the left must equal force times distance on the right. We know that Fred's F value is 3 times Barney's. So if Fred's force is 3 times Barney's, he's going to get 3 times as much torque. So in order for Barney to counterbalance that, well, Barney must have 3 times the distance. And that's pretty much the answer to this question. Whatever you do, Barney has to be 3 times as far away as Fred. Another way to look at this, Fred's distance from the fulcrum is defined as x. Barney's distance from the fulcrum is defined as y. So we know that the torque on the left is force times distance. We don't know the distance yet, but we know 1500 times x. Force times distance. On Barney's side, 500 times y is the torque. So we do know that 1500x equals 500y. And if we rearrange this equation, basically we divide both sides by 500 and then we divide both sides by x, we end up with 1500 over 500 equals y over x. So y over x equals 3. That tells me the ratio of y divided by x is always going to equal 3. No matter what y is, y divided by x will be 3. No matter what x is, y divided by x will be 3. That's their proportion. So that's telling me that y is always 3 times bigger than x. Barney's distance is always 3 times bigger than x. Alternatively, you could have picked a spot for Barney. You could just say, well, hey, I'm going to put Barney at, say, 3 meters. I'm going to put this side is only 3 meters. The whole thing is 6. I'm going to put Barney at 3, and the torque of Barney is 3 times 500. Force times distance. 500 times 3, and that's 1500. So how do you get the same torque for Fred? So you could set up an equation that way as well. There's many ways to do this. This you would have to use a little trial and error. And they say, what is Fred's maximum distance to keep the system in balance? Well, we know that the maximum torque Barney could generate is if Barney was at the very end. So the maximum torque Barney could generate is 1500. 3 meters times 500. So Barney could generate a total of 1500. Well, Fred is going to generate 1500 at a distance of 1 meter. Force times distance is torque. So 1500 force times 1 meter is going to be 1500. So again, FR on the left equals FR on the right. We're just kind of playing with these terms and figuring things out from there. And in this case, y always has to be 3 times greater than x. All right, let's do one more problem. A problem I really, really enjoy. Music time.
Interior crocodile alligator. I drive a Chevrolet movie theater.
What? Okay, so we got a little interior crocodile alligator popping. Chip the Ripper. So Mr. Sapone has you assist him with a physics demo, assuring you that you will be safe. You have twice the mass of the box filled with good stuff, but it is placed at half your distance from the pivot point, so it generates twice the torque, allowing you to balance perfectly. Is there anything wrong with Mr. Sapone's reasoning? Explain. So let's picture this out. There's a box, 25 kilograms, on a fulcrum, on a seesaw. You're 50 kilograms. Mr. Sapone says that you should sit twice as far away to generate double the torque, and that way you'll be safe. Does that make any sense? I don't know. We have to go through this. Is the alligator, the crocodile, going to eat you? So what we do need to figure out, first of all, that's completely false, which is odd because you would never come to a gruesome end in Mr. Sapone's physics problem. So let's keep that in mind. But in this case, what we do need to figure out is torque on the left and torque on the right. And we can do that because we have all this information. If you are going to be safe, if Mr. Sapone is doing the math correctly and he has you up here balancing to show a cool physics demonstration that he knows torque, torque on the left must equal torque on the right. And we know that torque is simply force times distance, or force times radial distance, force times radius. So Fr on the left must equal Fr on the right. And we don't have a force on the left and right, we have a mass. Remember, mass times gravity is weight or a force. So mgr on the right is going to equal mgr on the left, or mgr on the left must equal mgr on the right. So your weight on the left times your radius equals your weight on the right times your radius. And of course, gravity would cancel in this. You could actually get rid of it, but we're going to keep it in. So your mass is 25 times 10 times 2. That's 250. That's 500. And on your right, you have a mass of 50. Gravity is 10 meters per second squared. And you are 4 meters from the fulcrum, or the axis of rotation. And Mr. Sapone is telling you that 500 equals 200, or 2,000, I should say. That's not true. You're going to generate a lot more torque. So what's actually going to happen? The seesaw is going to go down, and you are going to get eaten by a crocodile. So these are our torque problems. Torque on the left equals torque on the right. You're just going to use this general formula. You can kind of, basically in some of the problems, you can make up your own R and see if it works on the other side. But really, you're just using this equation right now for these seesaw problems. And before we go, one more time.
Interior crocodile alligator. I drive a Chevrolet movie theater.